Welcome back to High Performance Computing. Today we have our practical lecture 5.1, and it's about understanding MPI communicators and data structures, and it's a part 2 already of this lecture. In part 1 of the lecture, we basically had some demonstrations, some practical hands-on demos really on how to do non-blocking communication MPI, really connecting also material we had before in lecture 4 and lecture 5 and so on, where we basically discussed a little bit that not everything needs to be blocking in terms of proceeding essentially with the process. Instead of, just waiting, we can maybe do something in between. That's why you would do non-blocking communication. But we also learned that, of course, this has dangers. So especially if you think about parallel performance and synchronization, which is an important part, of course, when you think about that many of our applications have this idea of using time intervals, of simulating something, a physical process, a physical phenomena. But usually we would have big loops and they always have a time step. And before then, every process in a very wild situation goes ahead while others are very slow, maybe are falling behind. We have to synchronize every now and then what we did with the MPI wait statement in context of this non-blocking communication. And then we learned this with the Cartesian communicator, that this is incredibly useful because the Cartesian communicator can help us to really do a scale out of the communication pattern, really, when you think about a 2D grid example that we had actually illustrated and then also have a demo on, where we can, of course, propagate a value very nicely, like the wave height, perhaps, or the wind speed to, let's say, one direction or a boat movement. It really depends on the scientific application. But the key message is that really the MPI environment then in this Cartesian structure can help us to understand what role do I play in this Cartesian grid, where I am in basically this Cartesian grid as process, right? And by doing so, we also learned the other side that basically by knowing where I am as a process, it's also important to know where my neighbors are and what ranks they have in order to do as a typical MPI send receive. And we learned a little bit that the communicator shifts, which suggests that you do a shift of data or so, actually is just much more preparing the communication really in the typical MPI send and receive messages that do the actual communication. So, and of course, material of part 1 is available in the video, but also will be fostered much more being part of assignment 2 for those that are taking the course. Now let's move ahead a little bit and put a little bit more emphasis now on the data side in this practical lecture. So in the last lectures, lecture 4, lecture 5, we already learned that data is, of course, a very important part of many of the parallel algorithms. And you have here in the second part of this lecture really 2 different types of it. So when we talk about the MPI derived data types, I still have the view very much on basically message exchanges. I want to maybe not send 5 times integers with send receive 5 times. Instead, I want to maybe do just one message exchange and just transferring 5 integers. So how I do this in a more efficient manner would be, of course, something we will learn. And of course, there are much more tougher data structures that many of you know from structs maybe in C and so on. So how actually combine different parts of it. The second part then of this part 2 here will be then more about parallel I/O. So why I need binary file formats like the hierarchical data format HDF. We will have examples for. There's a very similar one called NetCDF, which is also parallel I/O and binary file format. We will talk in later lectures about earth science about. So the principles are the same. However, the hierarchical data format has a little bit the idea of having, let's say, a file system inside the file system, which means the name hierarchical in the end. But those, of course, are better explained when I go to real life examples. So let's move ahead here a little bit, thinking about then what we had in these lectures to get you a reminder and revisit a couple of those again here. Short disclaimer that because of the time of demonstrating a lot here, I cannot go in all the details here again and explaining again what we had already in lecture 4 and 5. So if you basically jump on this video from the YouTube, basically I would refer to you looking more to lecture 4, lecture 5, and so on, or even lecture 3, where we started a little bit about this halo regions, right? When you think about this parallelism where we discussed here, and we basically want to have message exchanges, then how I do this, if I simulate maybe the weather or maybe the wave heights of the, let's say, coast here around it, I would do basically halos and ghost layers here. And that is what, of course, then reflects a little bit where we can also use not only Cartesian grid that we had before, but also where it now means we maybe want to have real physical variables sent in these halo regions in order to inform about something. Could be precipitation, rain, could be wind speed, could be wave height, could be lots of different entities, of course, in physics we're interested in order to compute then the accurate weather prediction as one example, or even boat movement, which is realistic given the current weather that we have, etc., etc. So again, the real detailed explanation is really in the previous lectures, and I would go here now a little bit into thinking this multidimensional data sets that we have in physics are, of course, very incredible important. And now when you think about that, you every now and then have a typical MPI send and receive information. We already learned the buffer, and this counting is in a way a representative of some form of memory structure in this buffer, right? So we also call that pointer to the memory buffer, so to speak. And here the data must be a bit contiguous in memory, and we will have here now 3 examples coming where you basically should shed the view a little bit how the memory layout would be. Once I have the memory layout right in that, I don't need to manually choose many of these variables, because I know in memory it will just follow suit. And this is one of the key ideas by working with this MPI derived data sets, while of course it is building on the basic MPI data types that you already know, right? So like MPI int and MPI char, but what happens if I want to have a message over the wire, which is a number of chars, or a string, what some people would you maybe refer to, or MPI int, I want to have a couple of integers over the wire. So let's go into this material and start with these derived MPI data types. And we learned the last time that usually it follows this kind of 3-type recipe here, right? First, you construct this new data type by using basically this dedicated MPI routines we already know, meaning you have to know what type you're really creating. And you see here, there's several different types. For the sake of time, I just have time to go in the first 3, but there are of course more than these 3 that I will explain to you here today and demonstrate. But it's really, that you build this new data types then with this construct based on the old data types, and then you have to commit it to the MPI environment. That's a very important step. So once you commit this new data type, this data type is known in the overall MPI environment. It is very important. And then, of course, you can use it in send and receive operation in the third part. And basically, it is a way of understanding really data. That's why it's data structure, really. It is this old data type that you kind of transform to really have this new data type, which includes a certain set of constraints in a way, but also understand directly the memory layout by having a very precise description. Where in memory can we find it, how many blocks there are really, and basically what I can interpret when I just get this buffer. And it helps with simplification really of many of the constructs, because you will see we really save lots of coding by doing this in this manner. So let's start with the first example here. And before I go to the slides, you see the slides capture the essence of what I will demonstrate in a hands-on experience. Let's move away from Cartesian communicators for a while. Not saying that they're unimportant, but here for the second part, we really want to focus more on data structures. Hence, we have some different ways how to do it. The first one I want to show you a little bit is the derived contiguous one. And as the name suggests, contiguous in memory already would ring bells of sorts for some of you. And contiguous C, you will read a little bit here the recipe that we already discussed. Of course, obviously, we will start with our MPI as usual, init and finalize. but then it already starts that we have one of our typical, let's say, simple data types from the MPI environment, a double here, created, which essentially is then basically our two integers I want to combine in one, right? And this is a contiguous. So you have two from the simple MPI type called MPI int, and I declare the variable here as a double int. Obviously, very simple example again, but instead of now basically sending and receiving one integer and another integer, the goal is here to say, let's send two integers at the same time. And I commit this to the MPI environment, as I said earlier, for simplicity. Or basically we have here send and receiving, which is basically the mapping of the roles if you do the enum. In other words, we have still, again, two roles to show you, demonstrate you a little bit the impact of these methods. MPI com rank, of course, is what we already know, and depending on the rank, I will be either send and receiving based on this enum that I have actually here defined. Not a big deal. It's a more kind of way of making the readability of the code a bit easier for you, that one is the sender and one is the receiver. So interestingly enough for us, it is, of course, now, let's say some numbers that we have to create here. It's basically two integers, just, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So basically we combine them as two integers. And we want to have some information out. What is the rank here? The buffer that is sent explicitly. Right now we have a send buffer pointer that we're going to use in the MPI send here, which points to essentially this buffer. And we said there are two integers. And because I say now 1, we cannot send these two integers unless we specify the double int type that we just committed to the MPI environment. And another thing you see, which is very relevant now, in the send, I don't specify any of the accurate, precise positions inside this buffer. I just assume that it's a contiguous memory allocation of this buffer of saying they have two numbers. And you see the difference here when you think about this printf statement. Here I did the other way around. Here I do manually selecting for 0 and 1, these two integers, right? So that's how you would essentially do it if you don't have access to the MPI derived data types. If you would do it in the traditional sense, you want to know what the values are, you would do it like this and specify the array index. Now, basically by sending this double type, MPI already knows and assumes that essentially these will be two integers, so there's no point of going into this business. So you simplify this a lot, but it's just pointing to this buffer that you're going to send. Now, of course, this works in a way in an interoperable fashion, so to speak, for the receive part of it. So you see here, we receive 2 for the receiver. When we do the MPI receive operation, we have this buffer here, which essentially is not initialized. So in other words, we don't have anything. And if this is working with these two values, I cannot give something out here, right? The received would be not initialized, would be not working. And the interesting thing is also for the receive part, we can use a double int type. And basically, of course, this is the normal operations we already know, the source and etc. Not so important here. And with this, we can now see if this really works. Our received buffer should getting these things out. And it also shows you that it works, that we just specify this buffer and don't care about the 0 and 1 we send. Indeed, we just have one type of a double int type, which combines two integers in one. And this is really the essence of this contiguous. And of course, if you need to do this, you can just have one send and receive, which is much more powerful and more high performance than doing not so a for loop of sending 10 integers or so, or 2 integers in a for loop with send and receive, because every message exchange carries a little bit of overhead, of course, right? You have to address the right processor, also on the lower level protocols inside the HPC machine. Now, for 2 sender and receivers, it may not be so dramatic, to do this in a for loop, but consider again that we do high performance computing usually with thousands of cores, if not 10,000 of cores and more. So for this, the overhead will accumulate of doing this, then at every processor would do this, right? And with this, we have here a very good idea of how you can simplify many of these codes and also make a much better performance in terms of message exchanges. And these are the knowledges that you see in many of the codes is not really working, especially of scientific domain codes where the people are not really MPI experts. You see very interesting behavior of this for loops a lot. And there will be actually one lecture where I talk about this typical errors of people that don't really have MPI experience. And that's why essentially you will find in many of the application experts today or simulation data labs that we have in Iceland or wherever you go in the world, that the scientific domain experts from neuroscience, from wherever in earth science and in machine learning, they team up with MPI experts with computing in parallel in order to make the code really high performance. But let us now come back to this. We want to have a subnet script here. That's what we know we always need. We assume we have two cores here. We make sure we have the right executable addressed here. And then let's go and do an S-patch on this and see how we're standing. This is a very trivial execution again on two cores. We see here it's already directly completed. We wait a little bit for the IO. You see here that's coming quickly. And I guess many of you can imagine this is a relatively straightforward part. So here it really worked that, of course, the send was easy to do. We just picked out of the buffer 0 and 1 in the kind of part of the buffer. But here we see also the double int work because otherwise I would not have these numbers. And I don't put them explicitly in the buffer array. Instead, we really received them as a double int type, which was the idea of the derived data type here. Okay, so I think the contiguous memory layout is obviously simple. You have to point to the start position in a way. That's what we did with the buffer itself. And you can imagine that this is, of course, often used. But what happens if we, let's say, have not a contiguous allocation of that? If basically we have a larger application and we want to have just subsets of data transport, which also happens because sometimes you're just maybe interested in a certain part of the Cartesian grid, or you're just interested in a certain part of, physical parameters, or whatever it is, what you compute. And the idea to understand this a little bit is by having perhaps a kind of use case and just summarizing here again on one slide what I just demonstrated with the MPI type contiguous. You have the output here, no big deal really. Let us go to a more practical application where you would say you maybe have a matrix of sort, which has, let's say, lots of information for getting an easier learning experience. We have here essentially just 0 to 8 as values. It doesn't really matter really. But what we want to send is maybe just essentially column, right? And of course, from the way of work now, how this is allocated in memory, we can assume that if you just point to this, there are two ways, of course, of doing this. With a matrix, we could explicitly or manually really get 1, 4, and 7 out, basically in order to get exactly these numbers. But this would be manually. And if you think about me doing this with 1,000 processors or a matrix which is 1,000 by 1,000 as an example, whatever, this is really cumbersome and you don't want to do this. So basically what helps here is to have the memory layout understood and tell the MPI environment maybe how we can automate this by using just the pointer to this buffer in a very specific way of creating another derived data type, which is called the vector. The MPI type vector obviously is a vector, as you see here. And here's the application example. So how we get basically this information out, we basically create a new data type. We call basically this vector here, or column really, because it's a column. And this is, of course, based still on different integers here. There's no surprise that 1, 4, and 7 are integers. So we want to combine the 3 ones, but we don't combine them contiguously as we have done just before. Here we have to extract the column. And in order to get to the column, we can basically have some idea and give this operation some idea how we actually can find these values in this bigger matrix. So you see this here, a little bit elaborated example on the memory layout in a way. So you would say that we have a matrix usually, which would be essentially then 0, 1, 2, 3, 4, 5, 6, 7, 8, which is contiguous and in memory, but we just picked with this block notion and the block length that you basically can do here now these elements out. So let's move a little bit to a practical example on the right-hand side, right? We say we have this column type that we're going to trade, and we say we want to have 3 blocks, right? 1, 2, 3. And of course, each of these blocks has just maybe one block length of 1. So we actually have just, one integer to transfer. Also no big deal. But of course, we also have to think about where it is. And with a stride here of 3, we can identify that every third basically layout here will be then the value that fits to the column type in this example. Right. So with this example, we have, let's say, a prescription how this column type is actually now picking the right values out of the big matrix, and could, of course, scale up to many different bigger matrices and so on. The stride, of course, depends a little bit how you create the array here. Right. That's obvious, I guess. If you have 1,000 by 1,000, you have to do another way of striding here. But in the end, it captures the way how you use the vector type. And you see here the sender, again, as in the previous example, takes a specific role, obviously, of sending later on a buffer. And you just see here the buffer that I'm going to initialize again as 0, 1, 2, 3, 4, 5, 6, 7, 8 that you see essentially here. I just don't want to specify now that I just sent essentially 1, 4, 7, etc. in the memory, because this could be elaborate, and you see how that would look like in my printf statement that I always give as a counter example here, right? In buffer 0, 1, buffer 1, 1, buffer 2, 1, I actually pick these manually, and you see it doesn't scale. If I have now 1,000, I have to add on, buffer 300, 1, 1, I guess you get the story. So the point is here we want to point to the buffer beginning, where essentially 0.1, where my, let's say, recipe begins of this vector, and that's all I have to do, right? It starts with 0, 1, and from there I use a column type, and the column type is already known by the MPI environment, saying, okay, if you point to this, we know that in 3 would be the next one size block, and in 3 would be again the next one size block, and I just use that for basically sending. Now that it works also interoperable with, let's say, not derived data types, so that you can still combine MPI derived data types with, let's say, the traditional way how you would do it is basically now the idea of showing you the receiver, right? You basically receive here 3 consecutive integers in this received from the normal type, and it's still valid because the pointer is accurate over the wire, and I receive this. And here I would do the manual way of actually then, of course, giving that out, right? In the received 0, 1, 2, I would assume my values here, which are then 1, 4, and 7. But now let's look a little bit, of course, this practical lecture, how that would look like in MPI. So let's look to the derived vector example here, where essentially you see that we have the same C code that I just show you and explained to you. Again, we have the sender part, the receiver part. We have this interesting new type vector, which we call a column, or column type really, that we use in the sending by just putting the point on the buffer 0, 1 without any specifics, right? That I do here with 0, 1, 1, 1, 2, 1, etc. So let's see how that executes when we have the received, and that should of course give us something out, because the received is initialized here, but essentially not with values. So if that would not work, we wouldn't see essentially the 1, 4, and 7 appearing. So let's see if that really works by, of course, having a job script executing this with 2 processors as an example here, and then pointing to the right executable. So sbudget with the submit derived vector. We wait a bit. We QStat it, it's already completed. So here we just wait a bit for the IO to follow really. And we see that the 33 that you have here in the QStat, that's already having the output. So let's look at this more. Again, double click on the name and then right click on the mouse gives you here and there a help of quickly look into the output. And you see here the sending was not a surprise. It would have worked because we have the buffer initialized. But we see in the receiving part, we have also 147. So it really worked to use essentially this new column type over the wire and then basically receiving it and giving it out here as a normal buffer in the receiving process. So also this was, let's say, a little bit more elaborate already, and can imagine that this is incredibly useful for many applications. And now basically we would think about what could be a little bit more interesting in science, perhaps here and there, which is a triangle of sort of a matrix, perhaps. And as I said, because of time, I cannot go into all the different examples of all the different MPI standards, but I think you get the message that these are incredibly helpful for certain patterns where you want to have some data of a larger data structure maybe transferred and then computed on. So here the example of the derived data type is very, let's say, more complex than the previous ones, because now I have to really specify more indices. I have a really indexed way of doing this. And you see how that could work in the example here, where you have 6 different blocks, and each of those have different, basically, block length and also different displacements. And here you have the full array where, you know, let's assume again in our simple example, this would be contiguous space, right? Essentially, again, allocated for this. But what we really want to send is not the whole matrix. We want the triangle here, right? 0, 3, 4, 6, 7, 8. We don't care about 1, 2, and 5 here. So how we now do this, extract that, the lower triangle, as we would say, is exactly how you could use this index data type. Again, this time I go directly to the code to make the connection here a bit more easier. We have this triangle type. We say basically the length of this is obviously 3, right? Because I see we can do this here in 3 different parts. And then, of course, specifying the displacement in contiguous space here means basically I want to have the 0. Okay, that's my first displacement, which is place 0. Then I have my second displacement, which is then at the 3rd position here. And then, of course, the third displacement is number 6, where we have then 6, 7, and 8. Now, obviously, we see this is block size 1, 2, and 3. That's why you see the block length here is 1, 2, 3. So 1's for the 0 space, 2 for the 3rd space, and 3 for the 6th space, to really get 3 types of what? In normal integers. And this index type now basically represents, when we commit this to the MPI environment, a kind of lower triangle that you can always extract from this array. So let's test this again, if that really works, because then we create a buffer again. By now, that's very obvious. We initialize it only in the sender. We do this MPI request, etc., to really, you know, perform then the message exchanges. But of course, in order to really see what's in the buffer, I do this manually here again. And you see already by having more and more values out of the matrix, it's more elaborate for me manually to pick these 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, which reflects essentially the position in this bigger, larger array. And again, if I have 1,000 by 1,000, you can imagine that would be much more work. So by doing this, basically, we learned already, I just have to put basically here the pointer to the buffer, and the buffer has just one type of the triangle type. Again, people might be thinking we would basically have 5 integers, so let's have a for loop of 5 to send 0, 3, 4, 6, 7, 8. Basically a for loop maybe with 6, sorry. But in the end, the point is that you have to do this manually then for each of these for loops. And instead, we just use one send operation with a new triangle type that has a recipe here above how it is created. It points to the memory. It has a memory layout which is basically showing you here the different displacements in the indexes that will basically enable us to point in this memory layout structure. So that it works on the other way around. You see, when we come to the receiver side here, again, our receiving buffer is, of course, oops, sorry for this. Our receiving buffer is initialized, but not really having any basically initial values. So basically, if that works, then we should get our triangle. If not, this would be crazy numbers. And by doing this, again, here you see a traditional way of really going index of all of these different elements that we will receive in order to show that I really received these 6 integers. That's why we wait here for the buffer size of 6 in the receiving part. So let's demonstrate it again to get a feeling for this. And you see also that, of course, these data structures get a little bit more complex over time. And let's see now basically how that is in the source code, which I just more or less explained already, just that you get the connection. Again, we have based on the rank, the different send and receiver roles that we basically will do here. And then we commit basically this data type here, which is a triangle type. And in order to send it, I just actually have to put the buffer in and say it's one triangle type, and all is clear automatically that I just take the triangle of this particular data structure that is in the buffer. Although the buffer represents, of course, the whole buffer, right? It's still the same variable here, but I don't specify the correct locations. I don't need that. I just have the triangle type that actually has a recipe here in the displacements and the integers and the lengths of the blocks, so that it takes automatically those. And of course, this increases the readability, right? Otherwise, and also basically here, the way how that works when you have maybe much larger basically data types. And the receiving end, we do the opposite. We just say we receive 6 integers. That's what they really are. And we basically give them out. So we have our submit script also with 2 processors, no surprise. We point here to the indexed version of this derived MPI data types example, and we'll also submit it and dispatch it. So here you see QStat says we are very quickly finalized. Also here, no surprise, of course, very simple MPI code. Let's wait for the output. We wait for the 34, and the 34 is not yet there. It also shows that IO sometimes has, of course, some let's say delay, but here it's coming. And essentially then having our triangle also in the receiving process. And that's really all I wanted to leave you on the table for the derived data types. I think the general modus operandi should be clear to you. Obviously, it is application dependent how you create those from the different types, and of course also on which buffers they will operate. But essentially, you have here 3 examples how these derived data types work. And of course, the assignments will also foster that a little bit when you do your own work with it. The final example, however, is a bit more elaborate, a data science example. And of course, learning clustering in 10 minutes and what we've done before is also not really possible. It will be established all over the course. There will be a lecture 10 where we go much more into detail what clustering is. Essentially, you can imagine that here there are these 2 kind of groups, and you see already with your human eye, so to speak, the Euclidean distance somehow makes these much more closer together than this, and you could say they form a cluster. A more elaborate version and procedure how you do this is so-called DB-scan, a density-based clustering with application of noise algorithm that we implemented in parallel. And you can learn more about clustering looking at this references or basically on the DB-scan reference. And there's a job script which is quite elaborate that we have to explain a little bit more, where you basically have the executable, of course, on one hand, into your different data sets. So we use Bremen, which means there is a certain data set that represents essentially laser scans of an inner city in Bremen. So there was a car driving through Bremen here, every now and then stops. At each stop, there's basically a 360-degree, almost, kind of shootout of lasers. And what comes back is lots of noise. You see here around the car, definitively on the floor and so on. you see the stops, but of course also in buildings here and there, windows which are not perfectly reflected and so on. There's definitively noise in it. And what you get is a big point cloud, essentially, of thoughts that you want to recluster depending on the buildings in order to recreate really the structure of this inner city of inner city of Bremen here. And this can be used for neurosciences. We already explained with basically cells in the same way. You don't have point clouds. You can use the HBD-scan algorithm maybe for counting here, basically drunken flies. It's a very interesting paper we have been involved with. There's 2 of my PhD students in the past where I use this Debugging clustering. And although we will discuss clustering much more in detail all over the course, it's scaling behavior. We already discussed a little bit the load imbalance problem of clustering. Here, I want to make the emphasis on the data structure, speaking of HDF5, because it is based on HDF5, and we will see there are some interesting parts of it when you work with these, let's say, high-level I/O libraries. Firstly, of course, it's binary, and secondly, it has basically a file system structure in HDF inside this file. So you have just one file, Bremen, but inside this Bremen file, there's different parts of it and different, so to speak, directories we will explore a little bit together. So let's go to the practicals here, to really, going also towards the end of the lecture today. We will be going to HBDB-scan. It's also interesting in many ways. Firstly, we use now not anymore a C code that is under our complete control. Instead, we're using a module, as I was explaining already before, to load the application, which is here the HBDB-scan MPI implementation. We have also relationships to the HDF5 in a specific version, because that's what we're going to use within this MPI code HBDB-scan, and hence we also have to load this in the environment. Here we specify 4 cores and would also go to different pointers of data sets. So if you want to really have a HPC case in the practicals, you can of course play around with Bremen, because Bremen is much more larger as a data set than the Bremen small. I quickly show you this here. The Bremen H55 is the original one with having quite much more points than this Bremen small clustered. For the sake of time, I show you a little bit the idea of Bremen small, but basically they look very similar. Now, the way how they look is now the interesting part of it. There's a certain point that you would imagine now, we looked in the output and in all data always was more. So let's do this with Bremen small, and we would be disappointed because this is a binary file. We cannot read anything here, right? And binary brings us performance. So we have to better stop this here because it doesn't help us. Instead, there's, for instance, different tools. Like here in HDF5, there's this interesting H5 dump tool, which enables us to look into the binary file basically with different options. And please have a look on this, and you will also do this in your assignment to really foster the idea what's the difference now between normal files and basically binary files. Now, one example how we could use this is now basically to make a HDF5 dump with, of course, Bremen small, and understand a little bit how it looks like. You see here the file content, and as I'm alluding to the group-based file system in a file system, we have here now colors, clusters, and Debugging. So we want to have basically an idea of different cluster identities once after HBDB-scan has done this. So this also means that when we basically would look into this now, of course, we can imagine changing a little bit here the idea from minus D really, and then looking to the part of clusters here, and want to have the data really, that what is inside. We see lots of zeros, which is nothing else than initialized, and then of course meaning that this is not any cluster ID, it's just initialized, and we're waiting for the HBDB-scan algorithms to really work. So let's execute this now. And you have seen that basically we have all zeros right now. And if you dispatch it and perform the clustering that we will also discuss, of course, later on in the course, much more in detail, how MPI is basically used, how OpenMP is actually used with hybrid programming in this particular code. But we have not even had the lecture on hybrid programming. That's why, basically bear with me. We will talk about this in one of the lecture later. But here is also a good example that sometimes a code can be also running, right? So not directly completed, because this is a elaborate example. It is operated, as you see in the submit script, only on the small part of Bremen, and has some interesting features with a minimum number of points to form a cluster and the epsilon neighborhood, as we call it in the DB-scan algorithm. Also more on this in lecture 10. But you could, of course, get different clustering results by playing with these parameters. And then, of course, if you want to have a real runtime of these codes, then you have to take the real big Bremen, so to speak, and not the small Bremen. But still, you see already that this is actually something which takes quite some time. It's already running since a minute. And while we wait, perhaps, for the job to finish, we can quickly review the slides that everything I just presented, including the binary problem here, essentially was more, all the content of the file with colors, clusters, and DB-scan. This is something, of course, what you also have here on the slide. But one thing I want to highlight is, of course, this part, right? You always have to do a local copy, because here we read and write into the file, right? You have seen Bremen small was all about zeros in the beginning. And of course, we assume that here, then when I execute this, basically with these different parts and this kind of different commands here, and this is a job script on a different HPC machine, not Uton, but it doesn't matter, it really captures the same essence. We would assume different clustering results here, depending on those parameters. And with this, also basically, you would assume that basically from all these zeros here, we want to have different cluster IDs, while not every data point here is maybe a cluster. We learned already, you know, if this here is a situation where the car parks, this is not a cluster. This is an error or noise, so this should be removed. And by basically filter that out, we want to have more or less the city of Bremen reconstructed. So let's see where the job right now is. In QStat, it's completed after 2 minutes. So, and let's look if we have something in the output, which is not the real output of this algorithm. The output of this is just meta information. It tells you how the cell space was created, how DB-scan was working in the local scans, and then doing the merging of the neighbors we discussed in once, where actually now the halo regions also play a role. Of course, it's a small data set, so there were just 21 clusters created and had a lot of noise points, as you see, but also very much cluster points. And the real output now, and this is important to understand, is not in the output file here that is readable. It is in the Bremen small itself. We have used it for reading all the points to know where in Bremen we are with laser scans, and it had a cluster ID 0 attached. Now, after, or basically during the runtime of this, we actually fill this HDF5 file again with values and update this information of saying what point is now basically belonging to which cluster. Obviously, we have to talk then about cluster IDs, and we use our HDF5 dump again in the form of clusters. And now you see here very little basically information in terms of exact numbers, but if you stop and we'll have a careful view, you will see that there's lots of noise points, as we know, but there are also some of the cluster IDs that we basically can identify from this. And of course, because it's very, very many points, it's actually hard to see them at once. That's why basically I created you also a slide on it, which shows the difference here. And when you carefully look and identify this, you will see, for instance, here is lots of noise, right? This is minus values here, which doesn't mean anything. But we have a point that is actually pointing to the cluster 4825. So with this, you have the identity we need in order to say that this clustering was working. So we have wrote directly into the file of the result of HDF5. And with basically looking on this binary file format view with dump, we could also prove it. Again, we will talk more about this interesting algorithm in many ways in later lectures during the course. Also, when we think about hybrid programming, so far we just did MPI. What about combining it with OpenMP? But OpenMP will be part of the next lecture. And then, of course, we can build on this in lecture 7, then when we then have the hybrid. So the final proof was essentially this. I think that's all what I leave on the table here for you for this particular example, and would say in the next lecture, we will talk about OpenMP, which is really shared memory. So we will have another view again of how to do power programming, and see you then.